Welcome everyone to VinAI Research Seminar Series today. And today we would like to welcome Associate Professor Tuyen Truong. And today we will also have Professor Hoài Nguyễn will be the moderator for our seminar. Hi Hoài, could you help me to introduce about the speaker?
Yes, thank you, Vin. I would love to. Okay, so good morning, everyone. Welcome to VinAI seminar. This is our first seminar in a while, and I'm very happy to say that our speaker has agreed to give a seminar in very short notice. And our speaker today is Dr. Tuyen Truong. He currently an associate professor in mathematics from University of Oslo. He graduated from Ho Chi Minh City University of Science with a degree in math and PhD from Indiana University. He currently working on both pure and applied math, and he target application in deep learning, and he's very interested in collaboration opportunities with VinAI as well as everyone in this seminar. Okay. And Tuyen, please go ahead. We're looking forward to the talk.
Yeah, thank you for inviting and organizers for inviting me to give the talk.
I have to say there should be a link for you for the audience to submit questions, and if you have any question, if you are in the call, you can just ask the questions. If not, you can send the question, and I will relay the question back to the speaker. Thank you.
Okay. Yeah. So it's my pleasure to talk, and I will share my screen. So can you see my my slides?
Yes, and
okay.
I see your slide, and I'm already impressed.
Okay, thanks. Yeah. So this talk is based on my joint paper with my collaborator, and so he works at Assoc AI research, and also in so this the papers, and then I have some other references. And now the plan of the talk is that first I will give an overview about optimization, in particular in deep learning, and then I present some theoretical results in both the deterministic and stochastic settings. And then I will talk about some practical considerations. One is to take care of when we want to implement the backtracking in deep neural networks, and then I will present some experimental results, and then have some conclusions and some ideas for future work. So maybe you know about this, but I will just give a very quick review about why we need optimization. So basically, first of all, we have data set and we want to give some predictions. First of all, we have pictures, and then we want to know if there is a cut or not. And if there is a cut, we can say, okay, the prediction is 0, and if it's not, then the prediction is 1. And so what we do is we try to collect a very big data set, and we try to train the computer. So then how can we train computer? And that is from an approximation theorem, which is about 60 years ago. And you can, for example, see in this overview paper on Acta Numerica in 1999. So roughly speaking, it said that if you have a function, then you can approximate it by a very special kind of function. And that, because it has that special kind, so we can easily do computations on computers. And what is this special form? So it has the form is a composition of functions like rho compose L1, compose rho, compose L2, where rho is a fixed function in one dimension, basically, and then L1, L2 are five functions. So five functions of the form like ax plus b, and here AB we don't know. We need to find A and B, and they are usually called weights or and biases. So we need to find them, and so how can we find? So basically we get a function which gives us a prediction, and of course yeah, so this our deep neural network will give us a function f x alpha, where x is the data and alpha is parameters, say for example the coefficients of the linear functions. And we want to find a good alpha so that it will give us a good prediction. And usually so that's the theory. So in practice, then we can use many kinds of functions, even they are not smooth functions. And of course, our function f x alpha, it will not be the same as the prediction. So it could be not of value 0 and 1. It could be some other real numbers. So what we do is we try to measure the difference between the prediction f x I alpha and the real value yi. And so there are many ways to do that, and it could be so that's, for example, we choose distance d, something like that, and then we take the average of the difference over all the training set, and so we get a function h alpha, which depends only on the coefficients, the parameters, and not on the data, not on the data set. And so then we have an optimization problem that we want to solve alpha, which minimize this h alpha. So it will kind of give us a good parameter which minimize the average, difference between the prediction of the neural network and the correct prediction. Now this is the problem. But yeah, later we see that of course this is just a rough approximation of what we actually do. Yeah. So anyway, so that's why we need optimization. And so then we can come to what kind of functions that we will need to optimize, in particular in deep neural networks. And so we can start first with convex functions, which is a very active field in optimization. So and it's very classical. So it's htx plus 1 minus t y less than equal t hx plus 1 minus t hy, or t in 0, 1, xy in Rm. The typical example is like x equal x squared. So a good thing about convex functions is that if we want to find minimum, then we only need to find to solve the gradient equals 0. So gradient is kind of the derivative in many variables. So yeah, so it's the very good property of convex functions. But so in general, many functions are not convex. So for example, we have this function z equal x squared minus y squared. It has a space of point which is called space set of point 0, 0. So this point is it solves the equation that the gradient of this function is 0, but it's not a minimum. It has in one direction is maximum, in another direction is the minimum. And it's called shadow point because this is what you see when you look at the shadow of a horse. And then there's another class of functions called C11L. And by the way, so this convex property is a global condition because you need this condition on the host space. And then this C11L condition is also global condition because we need the same constant L on the whole space. So it said that we say that it's C11L if the gradient is Lipschitz continuous with the Lipschitz constant L. And this kind of function is bounded by a quadratic function. So it's like fx will be bounded by x squared. And you can see this easily by calculus. And then there's another condition which is to compact support. It's also kind of a maybe okay. Yeah, it's also kind of a global condition. So it said that we need the sub-level sets. So that means the set of points whose values is less than equal given value or compact. So this is a good condition. However, we see that it's not satisfied by many functions which we see in deep neural network. For example, this function t to et over 1 plus et. This function does not have compact sublevels, or the function relu, which is max 0t. So it also doesn't have compact sublevels. Yeah, I should write compact sublevels, not compact sublevels. Then we come to another condition which is called the Loza-Searwitz inequality. This condition is actually a local condition because we only need this condition near 1 point. So this constant so kind of the difference of the function values are bounded by and to some power is bounded by the gradient. And here the constant c, we don't need it globally, we just need it locally. So it could be, if we take them supremum, it could be infinity. And this kind of function is satisfied by many interesting functions like real like polynomial functions or real analytic function like the function we saw before, t to et 1 over 1 plus et. Also, there are generalizations to non-smooth functions like yeah, for example, like maximum of some functions. And yeah, so like I said, so this kind of functions is very relevant to deep neural network because we see many functions we use in deep neural network, they satisfy this kind of thing. And then there's another class of functions which is well known in geometry called Morse functions. So this is a training condition, which means that if you take a random function, then it will satisfy this condition. So it said that it requires that all the critical points, so a critical point is a point where gradient is 0, non-degenerate, which means that if we compare the Hessian of the function at the critical points, then they are invertible matrices. So what's good about this function is that the set of critical points is discrete, which means that we don't have around every critical point is isolated. So around them we don't see any other critical points. And then, like I said before, this is the theoretic condition. It comes from theory called transversality, which says that if we have any function and then we perturbate it a little bit, and it will become most function. So, for example, you can usually in deep learning, there's a technique called LQ regularization. So we have function and then we add something like lambda x to the cube, and then after you do this, then maybe your function will become most function. And then another class is which is more general than most functions, is functions that all the critical points are isolated. Or yeah, so besides most function, we have also like real analytic function, because if we want to show that gradient equals 0, for example, you look at a polynomial function, and then the gradient will be for example, your function is in m dimensions, so you want to solve gradient equals 0, so you solve system of m polynomial equations in m variables, and by a so-called Berzou theorem. So usually you have only a finite number of solutions. So that's, I think, is satisfy this condition. Now there, of course, yeah, before we said that optimization is useful in deep learning. However, we don't use the usual optimization, but there's some special kind of thing. So I will review a little bit here. So usual optimization, we want to solve this. We have function f and we want to find global minimum. But of course, usually we don't know. It's difficult to solve global minimum, so we just want to find local minimum. Then in deep neural network, actually we don't do that, but we do something more special, more difficult optimization called the stochastic optimization. So we have parameterized function fx alpha, where x is random variable like the data set that we had before, and then alpha is parameters like the coefficient of the alpha functions we saw. And then we want to compare the expectation fx, small fx, with respect to this. Yeah, I should write the distribution of x, not alpha. And then let's see. Okay, so maybe here I change the the rows of x and alpha. Okay. Yeah. So here alpha is random, and x is so alpha is like x before the data, and then x is like the coefficient before. Okay. Sorry. Then this fx, we compare the expectation, and we want to find optimization to find global minima or local minima. But the thing is that usually we don't know about even the distribution, so we cannot compare fx, or even if we know the distribution, is still very difficult to compare fx. So then what we do is we don't compare this fx, but we approximate it by another function at each step. So at step n, for example, we choose randomly some values of alpha, and then we take the average. So this we call it we use this kind of approximation for our function fx. We don't know fx, and so then yeah, so this kind of stochastic optimization. And then optimization for deep neural network is similar to stochastic optimization, but we have some, but even it's might be more difficult. That's first thing is that we don't have an infinite data set. We have only finite, even though that's huge. And then so we cannot yeah. So then what we do is we will do like mini parts. So we decompose this data set into small parts. For example, its parts has the same size, and then we will use these mini parts to compute this approximation at n here. And then also there's another thing that yeah, so this the formula here. So similar to before, but now we use the mini buckets. And then one difference is that actually we don't want to find optimization of this thing, but we want validation accuracy. We want that is good. So we want good prediction. We not just want to optimize a function. So this is a difference to stochastic optimization, and that might be an explanation of some things we see in the experiment later. That if we use verbatim the algorithms, the theoretical algorithms, then maybe we don't get a good result. Also, one thing is that we don't, in theoretical results, we assume that we can run like infinitely many times, but in practice we don't do that. We only like run like 200 airbox or something, a finite number of airbox, and then we stop. So that's the difference. Yeah. So anyway, so that's this. So now we have optimization, user optimization, and then we have also stochastic optimization, and we have a kind of mini mass optimization. So assume we have an algorithm, optimization algorithm. So how can we apply to these different settings? So here is a general scheme that people use. So we assume okay. So this is for the usual optimization. We have function f, and we have an algorithm A, which what it will do is that it will choose randomly an initial point, and then at each step n, it will construct a new point xn from, for example, previous points x0 to xn minus 1, and also on the function f. So usually we don't need x0, xn. We only need xn minus 1, but there's some algorithms, well-known algorithms, where we need also x0 to xn minus 1. This is usual way to do this. So the goal is we want to, this sequence that we construct, it will convert to a global or local minimum. Now, if we apply to stochastic function, then we don't have the same function f at various steps, but we need to replace it by an approximation fn. So that's what we do. So we will apply the same thing, but now replace f by fn. And then it's the same for mini part. Okay, so I had an overview of what yeah, so about optimization. Now I will come to some optimization algorithms which which will be concerned in this talk. So first thing is and all of them are first order ones. So the first one is SGD, which is usually it would be stochastic gradient descent, but I also use it to call standard gradient descent. That's it's very old algorithm. It was introduced by Cauchy in 1847. And what it does is very simple. So we fix a number delta or bigger than 0, and then our algorithm will be like we construct xn plus 1 by xn and minus delta times the gradient of f at xn. So here's the picture. So the idea is like we are on a hill and we are at the point xn and we try to go down the hill. So down the hill means that we go in the opposite direction of the gradient. And so the main point is how can we choose delta? Of course, that's the idea, but we need to be careful about what delta we choose. Why? Because if we choose delta too big, then maybe xn plus 1 it doesn't it could go to the other side of the hill, and it may after that it may go away. Or if we choose xn if we choose delta too small, then maybe okay we still be go down, but very slow, and maybe we could not reach 0, but some points in between. And also this type of thing does not work if you apply for example the function fx equal x to 1 plus gamma, where gamma is some number between 0 and 1. And then you can check that whatever delta you choose, you cannot get 0 when you do limit. And this kind of function, even though it's not smooth, but we see that in deep neural networks we use many non-smooth functions, so maybe this could be relevant. And this is a Tendos maybe a simple scheme, but then there's some famous well-known modifications like Adam or momentum or NAT. And if you want to find more about this, you can look at this overview paper by Rutter in 2016. Now I come to backtracking analysis, which is the main topic of this talk. So it's also called Amiso's method. So what we do is again we go down, we go in the opposite direction of the gradient, but then we choose delta more carefully. So we not just choose any delta by a guess, but we wanted to satisfy a sufficient decreasing, that is fx n minus delta times gradient of fxn minus fxn less than equal minus alpha delta times the norm of the gradient square, where alpha is a number between 0 and 1. And if we assume f to be c1, then you can check by calculus that we always can find a delta bigger than 0, so that this Amiso condition is satisfied. And in practice, when we do this, how do we find this? So we just start from some delta 0, and we check this Amiso condition. If it's satisfied, then that's fine. So we choose it. If it's not, then we decrease it to like beta times delta 0, where beta is a number between 0 and 1. And if it's satisfied, then that's good. If not, then we go down. So b squared delta 0. So that's why it has the name backtracking. And because beta n will go to 0, so at some point it will stop, and this Amiso condition will be satisfied. So it's very easy to implement. Okay, so let's. Actually, this is interesting that this kind of Amiso condition has some similarity to what say the professional athletes like runners. So they do. So what they do is that they have a technique called aim for the sweet spot. So what they do is they try to improve a little bit at each time, sufficient improvement they have. And then you see here we have sufficient improvement in the value function like f x the next point minus f less than minus alpha delta the gradient square. So we have sufficient improvement. And then there's something called Wolf condition. I won't go to detail in this, but just say that this condition is more complicated than Amiso condition. So it needs Amiso condition and one more condition. This Wolf condition is quite popular used. Yeah, so I just say that later. Yeah, so this warfare condition is more complicated, but about the theoretical guarantees or the practical experiments. So Amiso condition is better. And then there's some kind of unbounded backtracking, which in backtracking, usually backtracking, we have delta or the learning rates delta less than equal number delta 0. But in this version, we can allow delta to be bigger than is to be unbounded. So delta could be like the gradient minus some kappa, where kappa is between 0 and 1. And so when it's close to a critical point, then this delta could go to infinity. And you can check this, for example, where fxy equal x4 plus y4. So you can check for degenerate critical points, and then you see that this unbounded backtracking, it allows we to have bigger learning rates. So it depends on if the functions in deep neural networks, whether we have the degenerate critical points or not. So if we have, then this might be better. And then another point is two-way backtracking. So in the usual backtracking, we start the search for delta n from delta 0, and then we go down. But that could be time consuming, because actually what happens is that if our sequence xn converges, then the delta n will, after sometimes it will become stabilized. It will be close to 1 over the norm of the Hessian, the limit point. So delta n are very close to each other after a while. So if we start from delta 0, then maybe we need to go down too much. For example, this is an example. For example, if delta n, we have the value would be delta 0 times beta 1000. But for delta n plus 1, it could be delta 0 beta 999. And if we start from delta 0 to search for delta n plus 1, we need to go 999 times. But if we start from delta n and then we increase it, then we only need to go by one. Just do one step. And here's one actual example I will show you. So here is this in this figure 2. You see, for example, if we do FreshNet 18 on CFAR 10, and we do for like we do this kind of thing, then you see that so what you see is the learning rate at each step, and you see that after about 40 steps, then the learning rate kind of stabilize. So you only need to like go up or down one step. So it takes a lot of time actually. And so let me go back. Yeah. Okay, so I need to go back. And then there's one thing that I said about subtle points before. Let me see. I said about subtle points before. And then actually convex function. don't have center points, but there are many functions that have center points. And for general functions, then Frey and Dean in physical review letters in 1998, they show that the number of local minima on the number of center points will becomes very small when the dimension increases. And then in the paper in 2014 by Dolphin, Askanu, Gaukli, Benzo, they did experiments, and they observed that we have the same phenomenon for functions in deep neural networks. And why this relevant? The thing is that because in deep neural networks the dimension is very big, like maybe millions or billions, and so usually that means we only see like subtle points. And so if we have optimization method which could be attractive to subtle points, then it will, most of the time it will run to a subtle point, because if we choose a random initial point, it would be closer to a subtle point because we have more subtle points. So that's the problem. So we should have an optimization method that can avoid subtle points. So for example, Newton's method, it does not avoid subtle points. So if you start Newton method, then it will usually converge to the critical point, which is the closest to the initial point. So if you start from something close to a subtle point, then it will converge to that subtle point. So Newton's method maybe not good for deep neural networks. Now I come to theoretical results for optimization methods. So we will see what we know about the optimization methods. So the point is that if we have an optimization method which have good theoretical guarantees, then that could be also a good method for using in deep neural networks. And so as we saw before, so we would like a method which have good convergence properties, and also could avoid subtle points. So here we start with the stochastic or standard gradient descent. So this is a typical result that if we sum f to be C11L. Yeah, we saw before that for standard gradient descent, if we have no bound on learning rates, then maybe we don't have convergence. So usually we need some restriction on learning rate, and to have that we need the function f to be in C11L, and then we choose learning rate delta less than 1 over, for example, 1 over 2L. So basically it comes something like it's bounded by 1 over L. And you can check by calculus that if we have learning rate satisfying this condition, then Amiso condition is also satisfied. So if we are in this situation, then we can view the standard gradient descent as a special case of Amiso algorithm. Yeah, I won't go into detail here, but you can check it. So here's, for example, here's a typical result that assume f in C11L and delta less than 1 over 2L, and f has compact support. And then also assume that f has at most countably many critical points, then standard gradient descent will converge to a critical point of f. And the idea of the proof is first we show that if we construct this sequence xn, and then if a subsequent xn k converges to a point, so such points usually called the cluster point of the sequence, then we want to show that it's the limit point is the cluster point is a critical point of f. So that's one thing. And then second thing is we want to show that the distance between xn and xn plus 1 go to 0. here in the Euclidean distance. And then when we have this kind of thing, and so we know that the cluster point is discrete, and then there's a result in general topology, which says that if we have a sequence Sn in a compact metric space, here the compact metric space we will use is a compact is the sublevel because of xn will satisfy fxn less than fx0. And assume we have the distance between xn and xn plus 1 go to 0, then the set of cluster points of xn is connected. And what's relevant is that if a connected set is discrete, then it must be a point. So it means that the whole sequence will converge to a point. And then we also have a good properties for avoidance of subtle points for standard gradient descent. And that's in a paper by Lee, Simchowicz, Jordan, Recht in 2016. So they so again they use the assumption that f in C11L and at most category many critical points and delta less than 1 over L. Then they saw that there's an exceptional set A which is small in the sense that the Lebesgue measure is 0. So basically what we care about this is that it means that it has a probability 0. So that if we start the x0 outside this set A, then the sequence n cannot converge to a center point. So the idea is to use the result in dynamical system, saying that if we have a center point and we have sequence constructed by this dynamic, so this is the dynamical system is here is the x maps to x minus delta gradient of f, and it says that if we have this thing, then and this if xn converges to this center point, then xn must be on a very small set on a proper manifold submanifold of this the space. And here it's like I said, so knowing L is important because if delta bigger 1 over L, then we have no guarantee. If we use backtracking, then we don't need to care about L. So there's a way for people to avoid checking this delta less than 1 over L. So they don't need to compute L by taking L delta n go to 0. For example, delta n equals 1 over square root n. So this is good in the sense that we still can prove some results like that. This is in a paper by Besekas and Tisiclis. But the point is, so it's good theoretically, but in practice, when you implement this condition, then you don't get. So you still get good performance, but not the best. So okay, yeah. So now I come to yeah, and then also if delta n go to 0, then you can also prove avoidance at center points. So this is in a paper by Panagias and Billy Uras and also Wang in 2019. Yeah, the same condition C11L and so on. Now, okay, I don't have time to talk about the ideas, but I say now for backtracking analysis. So what we know, actually, for example, convergence for backtracking analysis is very general. So in a paper by Axio, Mahoney, and Andrews in 2005, and for the non-smooth case by Artuch, Bonte, and Spicer in 2013, they proved that if F satisfies Lozada-Sierquist condition, Then and we construct Sn by backtracking, then either it's diverse to infinity or it's converges to critical point. And then in joint work with Hang Tu Nguyen, we prove the same conclusion for most functions, or more generally for functions with at most category many critical points. And okay, so I don't have time to talk about the idea, but we can also extend this to Riemann manifolds and Banach spaces. How about avoidance of such points for backtracking? So actually, we don't know. We don't know if I don't know if backtracking can avoid such points. But what I can do is I show that we can modify. We have modification of such points, which can avoid such points. So the learning rate in this will be in this modification will be like 1 over the norm of the gradient of the Hessian, which is kind of the best result, kind of the best choice you can choose for learning rate if you want to satisfy Amiso condition and you want it to have good convergence property. Now let me let's see. And so for Wolfram method, then yeah, the best we know is a result by Zootechnic, which assumes FC11L and so on, and then prove that any cluster point is a critical point. So if we combine everything, then we have a very general convergence and avoidance at certain point. For a modification of backtracking licence, which applies to a function f either has at most categorically many critical points or have or satisfy those quick conditions. So okay, so now I need to go. Okay, I don't have time to compare about second order methods. For stochastic settings, so what I can say that again, people need to assume like C1 on L and also convex CT, and also they cannot show pointwise convergence, but only like the convergence of the function value of fxn minus fx star, where x is a unique minimum. And there's some results, classical result in stochastic optimization. And then there's some result for backtracking, which again, yeah, under those kind of conditions. And before that, in 1998, there's a result by Tseng on the same thing. Now, what we would need to care about when we apply backtracking. So it means, like I said before, so mini-box optimization is, while it's similar to stochastic optimization, is different. So when we cannot apply verbatim theoretical results. And for backtracking, specifically, what we need is we need to rescale learning rate. So the thing is, we compute Amiso condition for one part, and that mini part might be different from the other part. And then here we still don't know, but we need to do like divide the learning rate we find from theory by something depending on the size of the mini parts. So that's one thing. And then the other thing is we should not overuse backtracking. If you use backtracking every time in every mini box, then you will get not good result. So now let me come to experimental results. So first thing is there's a Reddit link in about 2016 which said that okay, while like such algorithms used in optimizing neural networks and so on. And then there are people who explain why here. And then this is a paper in 2017 about workfare method. So they get quite good results here. You can see, but I don't know. And also in that link, in that Reddit link, they said they don't see any other teams that can repeat these results. For example, they have here CFA 10. They got about maybe 90% text validation accuracy. I'm not sure, but it seemed to be 90%. Then here, okay, here's what you get if you use the learning rate to go to 0. So you get about the same ResNet 18 and then CFA 10, you get about 84%. And then if you don't use this kind, you can get like 90 something percent. So this is good, but not the best. And now I present about some experiments for Backtracking. So here, first of all, you can see here's the last one, the ones with MBT, MBT TD, MBT MNT, MBT NAT. They are backtracking methods, and you compare with the user ones like STD, MMT, NAT, Adam, and so on, and you compare across all learning rates you use, and then we can see that backtracking NAT, it gets the best 93.85%, and basically it does not depend on the learning rate. So, but for the other methods like Adam, you see that if you choose like learning rate to be like 100, then you get only 10%. It's only good if you choose like about 0.001, where you get 92.29%, and then it decreases. So if you use the other methods, you need to use do manual, you need fine tuning to find a good one. Otherwise, it's not good. Well, for backtracking, you don't need to do that. You just put in, and then it will automatically find for you. And so here's what you get for validation loss for CFA 10 on ResNet 18 for different methods, and or the training time. So you see that for backtracking, then usually, for example, you get like you need like 19 seconds per epoch, but it's not too much compared to other methods. And then here you don't need to fine tuning, so actually it's better than the other methods. If the other methods you go from beginning, you don't know about what is the good one. And then here's the backtracking in a model which is not good for CFA 10, so it's the LeNet, but you still see that it does quite well. And maybe okay, can I have some like 2 or 3 more minutes so I can present more experiments kind of. So this is the one which is maybe interesting, is a toy model for protein folding. So it's so in protein folding, usually you have 20 amino acids, but in this toy model only two amino acids, and we have this kind of complicated function. We need to minimize, and this is the result. If we use backtracking, so backtracking is the back here, is the last one. So we see that it does quite well. So for example, if we start from some random point, then we get 13.963, and it doesn't go to infinity. While for if we apply like Newton's method, like adaptive cubic regularization, then it could go to infinity. Or BFTS, okay, BFTS in this example is good. Newton method can go to infinity, and then new Q is the one new method. Or this is so in this example, where in other dimension, 15 dimension for protein coding, let's see BFTS in one for initial point, it could go to infinity. The third point, yeah. In that case, also Backtracking might be because okay, and then also in the stochastic setting here, you see that Backtracking is it does not go to infinity. It's for example, here is the minibus size is 10, and this is the sigma. And so this is the distribution in n1 sigma, and the function is Kriya1 function. So Kriya1 function has a lot of local minimum, and the global minimum is 0, where the value is 0. And Backtracking works quite well if the sigma is big, like 1, and then we see that it could get the global minimum. And we see that it's when we increase the nn, the minima size, then Backtracking gets better and better. So for example, at the first, and then for 10, it gets 1.079 for the constant value. But when we increase nn is 100 and sigma square root 0.1, then it's decreased to 0.967 and so on. And it gets very good. Well, if you look at Newton's method, then it could go to infinity. So anyway, so that's I think maybe that's time. So maybe I will go to just a little bit about future direction. So what we could can we show that Backtracking gradient descent, the usual version, can avoid such a point? So that a question, theoretical question. Or for stochastic gradient descent, can we go beyond the assumption about convexity and C11L? Or we can prove pointwise convergence instead of only estimate the difference of function value. And then can we explain why we need learning rate scaling, and what learning rate scaling is better? So if we get square root of the size or only it. So usually people use n over n minibox, but in my joint paper we use square root n over minibox, and we found that our choice it gets better result for CFA 10 and on ResNet 18 and so on. And also, can we check? Of course, we didn't have people and resources to test this Backtracking for many different data sets and architectures. So that it would be interesting to do this if there are resources. And why is this worthwhile to consider this? Because as we saw, Backtracking is stable, so maybe it could be good when we add more data or when we want to against adversarial attacks, and and we don't need manual fine tuning, so it could save energy, which is good for money and also good for the environment. And so thank you.
All right. Thank you Tuyen, very much for the in-depth seminar on optimization. This is as I said, I'm very impressed with this paper and presentation style. It has been a while since I've seen this kind of presentation. Okay, so now we have a few minutes for questions. So if you are in the call, please just ask the questions, or if you are listening to the seminar from online, then you can type in the question in Slido, and then I will relay the question back to the speaker. Anyone who would like to ask the first question?
I have a question. So if I use backtracking with like agile method, I don't see the reason why it boost the performance.
You use
Backtracking and agile method. Yeah.
You want a combination?
Yeah. Because yeah, people invent agile method or whatever method to help boost performance of a previous optimization method, and now you invent backtracking, and I want to see if I can combine the two methods.
Yeah, okay, yeah. So I think that's a good question. So maybe I can first of all in the paper. So we combined backtracking and momentum, and also backtracking and energy. Instead of accelerated rated gradient. So and then we saw good performance. So I can show you again. Let's see. So maybe in this paper we have more. Yeah. So you see here, backtracking and energy got 93.85%. While if you only use NAG, so you got about 92.41%. So that's I mean that you can combine backtracking and other methods, but maybe you need to
slides.
What? Yeah. Sorry. Okay. So I need to. Yeah. Okay. I need to share screen. Yeah. Sorry. Yeah. Yeah. Here. Yeah. Okay. Can you see now?
Yes.
Yeah. So if you apply, if you combine, so the last slide here in this table 2, then you combine backtracking and energy, you got 93.85%. This is validation accuracy. If you look at NAG, so you got the best is 92.41%. If you get learning rate to be 1 over 10. So I mean that you can use backtracking with other methods, but maybe you need to take into count about the specialities of the methods, and how you can do this. For example, in so okay, so let me I wrote the paper by Rutter, and then so the paper by Rutter is let's check. And so what we do when you want to apply this, how can you combine backtracking and other methods? I will explain to you. I need to, let's see, put the, it's about 2016. Let's see. 2006. Okay. One, two. But okay, so
maybe it's you know.
Oh no, okay, maybe I just talk. Yeah, I don't need so that. So for example, in momentum or in energy, you have learning rate somewhere. So when you do it, so first you apply. So usually they will fix that learning rate. But when you apply backtracking, what you do is that first you apply backtracking to find a good learning rate, and then you put that learning rate into the scheme for possible energy, and then that's what we did, and we got good performance here. Also here, if you use other, yeah, let's see where is it? Yeah. Or in momentum, you also have a place where you have learning rate, and then you put in you first you use backtracking, and it will give you a good learning rate, and then you put that learning rate into the formula for momentum, and then you get a good result. So for Adam, it could be a little bit difficult because you need to decide what's the learning rate in that Adam, and then you use this type of thing. Yeah, so it's
so if I look at this table, so in
yeah.
practice, most of my students would do is they use multiple learning rate. They start with something relatively large, and like after 100 epochs or whatever, they keep reducing by like a factor of 10. And that seems to be a normal practice these days.
Oh yeah. So I understand that. So that thing is I think what you're doing is you delta n go to 0, because in that case yeah, because okay, maybe
in practice it doesn't go to, it's like they start from 10 to the -3, and then they go down 3 times or something like that. And
yeah, it doesn't go to 0 because you only do like 200 above, right? But if you do infinitely times, and then you after like some above you decrease a little bit, and then it will go to 0.
Right. Yes.
And I think the main idea behind that is that you use the result by, I mentioned before, by like basic cards and the sick. I don't remember his name, but the secrets that they saw that, or maybe even the result by the classical result in the 1950s, 60s. That if you use learning rates go to 0, then you have convergence. But then the point is that yeah, so maybe yeah, maybe if you just stop after like 200 above, then yeah, maybe you still get good result. But how can you explain it? So if you want to explain it, you need to use that learning rates go to 0, and also but then we saw that if you use learning rates go to 0, then like in the paper that I saw you, that paper was in 2000. What paper? Yeah, I can show this paper.
My question is, I see the comparison table that you compare with a fixed learning rate.
Yeah.
How would it compare with decreasing learning rate in terms of empirically?
Yeah. So decreasing learning rate. Yeah. So that's what I just want to mention. So then I show you here. So you can see here, if you want to use purely decreasing learning rate, so you can see this paper by Metikopoulos, Halak, Kavis, stochastic gradient descent in non-convex problem. I think it's problems. So here what I got: accuracy, training accuracy, test accuracy. So they got about yeah, test. So if you look at the figure of D, so they use the purely learning rates go to 0, and you see that they got only 84%. So the point is maybe sometimes, or for some data sets, you could do like where you say, okay, I will choose first learning rate to be like 1, and second learning rate to be 1, and third learning rate 1/2, and fourth learning rate 1/2, and so on. And I got good result. But how can you explain it for general data set, or can you apply the same thing for the general for general data set, or do you need to like fine tuning learning rates for each data set? So that's the point. The point of backtracking, that you don't need to need to do any experiments. You don't, if you are a user, you don't need to know anything about optimization. You don't need to do any experiments. You only need to put this optimization in, and then it will give you the result, and the result are usually very good. So and then the comparison. So why did we do comparison like this? Because okay, where's the I saw again the table. Because we want to show that if you apply backtracking to an optimization method, then you get a better thing. For example, here I want to apply backtracking to gradient descent, and then I saw that okay, so for gradient descent, then maybe backtracking not it's not it's not better than stochastic gradient descent if you choose correct a correct learning rate for stochastic gradient descent 1 of 10, where you get 92.07. But the point is, how could you find 1 of 10? So you need to do a lot of experiments, right? So if, for example, if you start not at 1 of 10, but at 100, and okay, you could say that 100 might be a big number, but actually we don't know, because it depends on the data set. Maybe for some data sets, 100 could be a good number, so you don't know. Or you can say 0.001 is a good learn rate because it's small, but if you look at this table, it's only 54%. So the point is, you don't know what is a good learning rate. You need to do experience. So you need to spend a lot of time doing this kind of fine tuning. While for even for backtracking for gradient descent, MBT-TD here, you get a bit less, but just a little bit less. But the point is, you don't need to worry about this fine tuning. And then if you apply backtracking, so we saw that if you apply backtracking for NAT or MMT, then and it's very stable, and you got good results. So you get 93.70, 93.85, and you don't need to care about what learning rate to choose. So that's the point.
Okay, thank you. Yeah. So,
yeah.
I think we are running out of time, so maybe we have time for one more questions. And anyone would like to ask the last question? So in terms of the overall times and or the function evaluation, how is this compared with the normal SGD?
Oh yeah, so yeah, I think that's a very good question to think about. So let me share the what we got. So we didn't know. We didn't do the comparison about function evaluations, but like I showed you before in this picture, that so for example, if you look at beta p here, so after a while, so you expect that you need to do not too many function evaluations, because you only need to go like 1 or 2 steps back and forward, so not too much. And then this is for Mexican heart. So this is what we expect from theory and experiments. And then here's what we saw with what we saw with this is the time. So you can see so the STD is the red, so it's in the below. It's about 16 seconds for an airbox. And then the backtracking gradient descent, which is the blue with the triangle. So it is here somewhere. I think it's here. This one. So it's about I think 16.3 or 4 seconds per airbox. So it's not too much different to gradient descent to STD. And then if you look at backtracking NAT or backtracking MMT, then they take a little bit more. So here they are above, but not too much. So they only 19 seconds, about 19 seconds per airbox. So not the difference, not too much. In particular, if for example, if you apply STD from scratch, so you don't know what learning rate you should use. So for example, at least you need to like test this with at least 2 learning rates. So you would need to spend like 32 seconds per airbox. Well, for if you apply backtracking, you don't need to care about learning rate. So you need only like maximum like about 19 seconds per airbox. So I would say backtracking is better if you take into account that you don't need to do manual fine tuning.
Okay. Thank you very much. And yes, unfortunately, we're running out of time. So, but let's thank the speakers. It's all online, so we cannot clap our hands. But thank you very much.
Yeah. So thank you very much for your attention, and yeah. So please stay safe and sound. And if you have questions, you can ask me directly, or if you have comments and so on. And,
thank you.
Yeah.
Yes, and thank you, everyone.
Yeah.
Bye.
Yeah. Bye.